Okay, well, thanks for showing up today, everyone. We're really excited to have you here in attendance to go over our causal modeling release webinar. So here at Novi, we've been in business for 7 or 8 years now doing data science in the oil and gas industry, and this is probably the biggest algorithmic update we've had in our history. So we're very excited to be walking you through what we've done here on causal modeling and to kind of show you some of the results and the thought process behind it. And as I mentioned before, we do have the chat open. I will be taking questions both live and at the end. So if you have anything, I'll be monitoring that as we go, and I'll answer it if it's relevant. And if not, we will have plenty of time at the end of the webinar for questions. We scheduled this for an hour, but I definitely don't have an hour of material. So I'd love to spend some time just kind of chatting about things after we go through the material. Okay, let's get started. So first off, the key question, why are you guys here? Why is spacing so important? Interwell spacing and stacking is probably the single biggest CapEx lever that operators have in modern unconventional plays. They have still a wild divergence in the designs that they're implementing. So down here, I'm showing you a time series over from 2015 through today. That shows you the average density drilled by operators in the Northwest Midland Basin. I've just selected a few of the top operators here. And you can see that these operators range from, anywhere from 10 to 20 average wells within a 2,500 foot radius. That's a tremendous variation right there. Literally twice the CapEx up here at the top compared to the bottom. And if you're a modern operator trying to decide what to do to develop your acreage, you have let's say you're thinking about in the top right here, a 1,300 foot lateral spacing development, 2 zones at $10 million a well, that would come to $80 million in CapEx. But if you ramp that all the way up to 660 foot spacing for a 3-zone development, that would be $240 million. So it's really a tremendous range in terms of the capital expenditures involved here. And if you drill too many wells, you end up destroying value. If you drill too few wells, you're leaving valuable money and reserves on the table. And that's the core of the problem here for spacing and parent-child questions. And then the second key thing here is that it's not just a question of your co-development. I've shown you a very simple cartoon over here on the right, but in reality, you have parent-child relationships that make everything more complicated. You have maybe you have 2 wells that are already on the unit. One of them's in some upper zone, one of them's in some lower zone. How do you infill around them? And that also interacts with the other decisions that you have to make as an operator or as an investor to develop your unit. And I want to just take a moment here to reset on the spacing story itself. So, for those of you who've been in the industry for a few years, you all probably remember the Dominator pad back in 2019, drilled by Concho in New Mexico. And here I'm showing you a Wall Street Journal story, shares in top shale driller fall after it discloses well problems. And really, this is about that one individual pad. And the downspacing tests that were occurring back in 2018, 2019 really became the hottest topic within the industry and spilled over into the broader investment community as questioning the ability to drill these really dense developments. But even within just this one development unit, the story is more complicated than probably you remember just from the headlines. So over here on the right, I have a gun barrel showing you the Dominator unit. And in the bottom here in red, I have highlighted the 2019 developments, which were targeting the Wolfcamp B, Wolfcamp A, and the Third Bone Springs. And ultimately, even though these, this pad resulted in some bad news, the wells have kind of recovered, and now we're forecasting them to have a 50-year EUR of nearly 70 barrels a foot, which are really actually fantastic wells in the grand scheme of things. But in 2019, they did that primary development. In 2022, they came back and returned to drill an additional 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 wells. There was one of these was apparent. 11 wells they came back and drilled above the existing Dominator development. And these wells are monsters. They're going to cum, we're forecasting over 94 barrels a foot on average, which this slide in itself should have you guys questioning whatever the dominant narrative is on spacing. So really, I just wanted to hammer home that spacing and parent-child, it's a complex problem, and there's a lot of opportunity within that complexity for sophisticated operators to be successful. So spacing is important. It's obviously the key decision that operators have to deal with. Why is it such a hard problem? And this is really where we get into the motivation for us working on these new algorithms. Over here on the right, I'm showing you one map is our spacing wells and radius, the same measure that I was just showing you before, where the red well sticks are denser developments and the blue well sticks are more widely spaced. And then to the right of that, I'm showing you our measurement of rock quality. And red is better, blue is worse. And you can kind of very clearly see, you overlay these two on top of each other, the best stuff in the basin in terms of rock quality is not coincidentally the same place where the operators are drilling the densest developments. And what this ultimately ends up creating from a data science perspective is entangled variables where there is a lot of mutual information between the reservoir quality, the spacing design, and also the completions intensity, which kind of tends to follow the same patterns here. So in combination, you have really a difficult data science setup for understanding the impact of spacing, at least if you're looking at a regional level using an inferential approach. So there are a number of ways that you could tackle this. You could look at physical modeling, you could fix it to a certain recovery per section. But really, here at Novi Labs, we're in the data science business, and we wanted to use a data-driven approach. So the question then is, how do you actually learn the impact of spacing, given that the data set has a significant amount of bias? So how do you disentangle spacing from completions and geology? So we are leveraging here in these causal models the research field called causal inference, which is about estimating the impact of a treatment on a population, even in the presence of confounders and other interacting variables. So one, maybe a more legible example for you guys that you're more familiar with, imagine you're trying to estimate the effect of some kind of a medical treatment like, I don't know, an improved diet on a population. And if you're looking at the impact of, let's say, red meat on the diet of a population, within an epidemiological data set, like if you're just surveying what everyone's eating and comparing that to their health outcomes, you have a lot of other things that are maybe going alongside the presence of red meat. Maybe that means they're also eating a lot of processed foods. Maybe it means they're, they have certain income brackets that they're falling into, or they live in certain parts of the country or certain areas within a metropolitan area, or more rural or more urban. Maybe they're higher presence of smokers. All these different confounding and interacting variables make it so that estimating the impact of dropping or adding in red meat is difficult to understand just from the epidemiological data. So the good news, however, is that public health and economics have developed a causal inference as a way of helping to disentangle this challenge by controlling for intergroup differences. And within public health, maybe you can actually assign people to a diet, but we don't necessarily have operators out there just running counterfactual examples for us on developments. And once a unit's developed, it's developed. So we're going to have to leverage what's within the data in order to understand the effect of pad spacing as a treatment applied to a known completion size and geology. So speaking a little bit more here about causal inference itself, the simplest approach that you could take would be stratification. So if I take a look at like my Y versus X over here on the right, you can see that if I just look at the entire population, I might get one idea of the trend. But if I stratify it into these 5 different groups, which I've, this nice Wikimedia Commons person color coded here, you actually see a different effect when you're looking at an individual level. So just to give you a rough conception of what that would look like in a very simple sense. But this has some issues where if you have many different variables, this approach isn't necessarily going to isn't going to necessarily work very well. And there's various other assumptions that went into this. So we really need something which is more sophisticated for our oil and gas unconventional development problem area. So when we were deciding to do this work here, we looked at a bunch of different causal inference approaches and ended up using what's called double machine learning. If you want to learn more about it, you can go read this Chernozhikov paper 2018. You can look it up with the title down there. But this approach actually dates all the way back to 2016, and it uses complex nonlinear models to do the debiasing. And once you have debiased your data set, then you can create an accurate estimate of the impact of the treatment. The nice advantage of this is that you can deal with both multivariate inputs and outputs. So this approach means that we can work with multiple different geology variables, completions variables, and also spacing and parent-child. Like there's no theoretical limit, only a practical one, which in our experience, when you're dealing with the complexities of unconventional developments, multiple zones, parent relationships, child relationships, it really does help to have many different possible variables that you can be leveraging to describe what's going on in the subsurface. So with our double machine learning approach, we have now implemented an algorithm that's available to all of our analytics customers. I can walk you through this if we have some time here at the end of the discussion. But within Model Engine in the parameters advanced screen, there is a model type that you can select, and you can choose Novi pre-drill causal. So that's for anybody here, which is a Novi user. That's where you can go get it. So the other couple things that I'd like to highlight here that are part of our causal inference package that we've had to implement. One is that we've added a method for estimating the Shapley value contributions of the treatment parameters. And if any of you work with us or have seen our stuff out there before, any of the papers or the stuff that we share in public, we really leverage Shapley values as an explanatory data set heavily. And so these are extremely important. So for instance, over here, I'm showing you a Shapley plot for the closest 4 neighbors, average distance, and for the parent age, impacting on barrels of oil per foot at 10, I think this is 1080 AQ. So you can see how those are impacting as you bring the wells closer together. You lose that production, whereas the parent gets older and older, you also lose that production. The other thing I'd like to highlight here is that the treatment effects are not estimated in a vacuum. They are influenced and evaluated in the context of the other variables that are present. So for instance, I have the fluid intensity here in barrels a foot. So the dark dots here on the screen are wells that have a completions treatment that has a lower fluid intensity, and the wells with the greens and the yellows have a higher fluid intensity. So you see that variable interaction captured by our algorithm. Yeah, the other thing that we have that I want to highlight is that we do have hyperparameter tuning that is done by a multi-objective evolutionary algorithm. So rather than just optimizing our hyperparameter tuning process on a forecast accuracy objective function, we're actually evaluating it simultaneously on accuracy and spacing impact. So that's pretty powerful. We do have one question in the chat, which is how much error does the debiasing step add? The answer is actually these models are more accurate than our baseline models. So it's not a huge effect, but they have a slight accuracy improvement over, let's just say, a pure decision trees based algorithm that we would use for our main forecasting. So we weren't sure when we initially began this work whether or not there would necessarily be a trade-off between the model sensitivity to spacing or parent-child and the accuracy, but we have found that they're actually more accurate. And the other thing is they are especially more accurate for super dense developments or other things that would have been harder for our initial algorithms to evaluate. So good question. Thank you. Okay, now we've actually had this algorithm out there for a few months here for some of our customers. So I did, you could take it from me, but I did want to share some things that we've heard from our customers themselves. One told us that this matches the empirical observations for production impacted downspacing wells. We had a customer up in Canada who said they're seeing much more realistic spacing degradation in their gas stream. And a Delaware customer told us that these algorithms prove superior for their analysis of stacks and staggered neighbors. So thanks to the customers who gave us those votes of confidence. Ultimately, that's the real measurement for this thing is how our customers can actually use it in the wild. Okay, so now I'd like to walk you guys through a few examples here and show you kind of some ways in which we're using these causal inference models to drive business decisions. And let me take us a minute here and explain the chart that I'm showing you. This is basically 3 gun barrels stacked on top of each other. So I have 1 gun barrel down here in the bottom, 1 gun barrel in the middle, and 1 gun barrel on top. And the top gun barrel is 8 wells a section. This is basically, I'm showing you a half section. The middle one is 10 wells a section, and the bottom one is 12 wells a section. And if you're, joining us from somewhere internationally, a section is a square mile in colloquial usage here based on the US land grid. So really where it's per section, that means per mile distance. So just a little quick translation there for you guys. This model was trained on 12,000 Midland Basin wells, 23 features. This included subsurface completions and wellheader. So across these, and then we take that model and use it to forecast these hypothetical developments. And each of the dots here that you're seeing on the screen, the red ones are a Lower Sprayberry, the orange are Wolfcamp A, and the yellow is a Wolfcamp B. So 3-zone development. The highlighted numbers that you're seeing marked on all the different wells on the screen are the forecasted EURs from our causal model. And what I'd like to highlight here for you guys, let's just for a minute focus on these exterior wells over here on the right of the pad. As you bring them closer and closer to their neighbors, you see those EURs drop from 59 down to 53 barrels a foot for the Lower Sprayberry and 34 down to 31 for the Wolfcamp B. But you see a bigger impact in the interior wells on this development, just as you would expect, where you have, number one, a much higher EUR for the exterior wells compared to the interior, where our 8 wells a section, we'd have more like 43 barrels a foot, 34 and 26. And then as you bring the wells tighter and tighter together, the 12 wells per section, we're down more to like 35, 28, or 20 for our EURs. So we're picking up that nice complexity between exterior and interior wells under a downspacing scenario. Okay, next up I have a parent-child example, and this is another optimization question where we are taking an existing pad and we're moving an infill pad closer and closer to the parent stepwise. And the top row that you have here, that's 660-foot spacing. The bottom one here is 1,540-foot spacing between the infill wells on the left and the parent wells on the right. Actually, I got that wrong. Parent wells on the left, infill wells on the right. And so we're tracking, you see the highlighted well here would be the infill well that is closest to the parent wells. So what does that EUR look like when the infill well is 1,540 feet away? And then what does that EUR look like when the infill is only 660 feet away from the parent? So this is isolating the impact of that parent distance while we are maintaining the co-developed distance with the other neighbors constant. So over here on the right, I'm plotting those Lower Sprayberry and Wolfcamp A EUR degradations for you. So that goes from the Lower Sprayberry from 56 down to about 38, 39 barrels a foot. And the Wolfcamp A goes from 51 down to about 34 barrels a foot. So 30 to 33% degradation just by changing the distance to that parent well. So these are both kind of independently key levers that you have as an operator. How are you developing around your parent wells? And then, like we just previously showed, how you are developing your infill or your co-developed wells that you're drilling afterwards. So I've been showing you EURs so far, but really it's when we're making our forecasts, we're making time series forecasts, and the models generate different forecasts and different sensitivities depending on the age of the well. So here, for instance, I have 3 sets of wells for the Lower Sprayberry, Wolfcamp A and Wolfcamp B. The most tightly spaced wells there are in the yellow, and the most widely spaced wells are in the black there. And you can see that if you look at the early time for these wells, there's pretty close agreement between the forecast for each of these different groups. Whereas as you get out to later and later time, the spread between them widens. And this is something that you'd want to see, and it matches the observations where a lot of times your tight developments, at least in the Permian, may look really good for a few months. And then after that, you start to see that divergence in performance. So those are all numbers for production units. Really, at the end of the day, we're not in the oil business, we're in the making money business. Everyone likes to see some sort of a chart like this, where you have your total unit development density on the x-axis and the total unit value on the y-axis. And of course, there are various different ways of deciding how to do your development density on any given unit, but this is a very common and often used one for making that decision. So as you add in wells, even though the individual performance decreases, they still may be adding value to the entire unit. But eventually, as those wells become less and less profitable and possibly even negatively valuable, the incremental wells, then you start to erode the value from your unit, which is the basic concept in this type of a chart. So what we see here is that the total unit value goes up from 6 wells a section, it's right around 20. And then if you triple that to 18 wells, it's 43. And then incrementally beyond that, you're starting to really degrade the net present value, even though you have increased capital expenditure. So you have, you're not making money. You're not making money on those incremental wells. And depending on your cost of capital, availability of oil field services for D&C, and whatever your business's preferences are, obviously you might be choosing a different development density based on that. Okay, it looks like we have another question in the chat here. Have you run this analysis in areas with high natural fractures versus low natural fractures, and how that affects the performance of a wide versus narrow spacing? That is actually not something that we have done, but if you had a map showing you the incidence of natural fractured areas versus low natural fractured areas, that is certainly something that you could put into our models to show the impact. Because yeah, I mean, Jesus, I agree, that does seem like something that should have an impact on the performance. You would certainly expect it to. Yeah, good question. Okay, now I have this is hot off the presses. I was just wrapping up this map yesterday afternoon, so you guys get to see a little something new here. But this is our regional. We built a regional basin-wide inventory for the Midland Basin, and we used our causal model to forecast the developments. And what you're seeing here on the map are the remaining Lower Sprayberry, Wolfcamp A, and Wolfcamp B developments that are infill above or below the primary zone, which has already been developed. So this is showing you the forecasted, above or below infill or return performance across the basin. And I'm excited to be able to show you guys this because it's actually, before we had these causal models, it was difficult to build a model which was both very good at capturing the regional geological variability and capturing the spacing and parent-child relationships. But now with these causal models, we can build those models that allow us to do these type of inventory analyses and to properly capture the spacing and infill effects. So when I'm coloring the sticks that you see on the map here by the EUR, not EUR, these are 3-year cumulative oil per foot going from 11 up to 29 barrels a foot from the red to the green. So that's the colored sticks on the map. And over on the right, I've hidden the labels here, but these are the counts of those infill return opportunities by the operator. So, and they're colored by the quality of those infill return opportunities. So some operators have a lot of these higher EUR, higher performance well infill opportunities, whereas other operators do not have a lot of these available to them. So, going back to like that Contro Dominator pad that I showed you up at the very beginning, certainly infilling above or below primary developments is a potentially rich way for operators to extend their runway. And these models allow you to evaluate that both for any particular individual unit you're looking at or for more of a regional basis. Okay, so we have a couple questions here in the chat. Thank you guys for dropping that in here. So we have one question from Samuel Rogers about the Wolfcamp B changing as well density increases. So we have the total unit NPV on the y-axis and the density over here. So the question is why is the Wolfcamp B changing compared to the other wells, differently compared to the other wells? And really it's about the unit economics here. So the Wolfcamp Bs are really negative value, incremental value beyond that point, whereas the Wolfcamp A's or B's are, the incremental wells are right around break even. So that's why you're not seeing nearly as much change. And this, I just ran this at I think $65 a barrel or something like that. But this will also change, obviously, depending on your price model and your cost model. And then we had another question from Oliver Rojas. Is there a validation process to confirm that geological factors are influencing well spacing, or do some operators use a fixed spacing regardless of drilling zone? Yeah, so we, whenever we're generating these forecasts and we have the treatment variables, like you can see here, the different treatment effects for the spacing variables, those are going to be driven by the geology, and the completions design are going to potentially affect, if there is data-driven evidence for it, potentially affect the treatment design that you see here. However, that doesn't get you to actually what the operators are deciding. And I think that's really, it's a different question, is what actually influences the spacing compared to what operators are deciding. And when we have been doing our evaluation of development density and things like that, like in the Midland Basin, even though I shared you this chart, these operators are in kind of the same area, but they have a pretty wide spread in their development density. But if you go to like the Delaware Basin, it's even crazier. Operators in the Delaware really don't follow their neighbors nearly as much as they do in the Midland Basin. So you have less of that. You have less consistent development density in the Delaware compared to the Midland Basin. Other plays like the Bakken tends to be kind of somewhere in between, where you have some influence of what other companies are doing in the area, and then you have some difference from company to company. And I think the other thing, in addition to just the geological factors that are driving that preference for one development density versus another one, is also related to the operator's economic preference for more value maximizing or more rate of return metrics. That will definitely push you more to one end or another of the development density, just for what you care on a corporate level. Okay. Got a lot of questions. Got more questions. This is good. Okay, Charlie says, have you all thought about identifying the optimal scenario where you come back and infill above existing development versus a situation where you wouldn't want to do that? Yeah. So we are actually really doing a lot of research into this right now, Charlie, because we do have, as you imagine, like the infill return development is extremely important to the go forward inventory of the basin. So some things that we're looking at are co-development versus infill. Doesn't matter more filling in above or below an existing development. And in a lot of cases, as an operator, you may not have a choice. Like if you've already, if you've already drilled in and, the Wolfcamp A and the Wolfcamp B, your options are, do you want to drill above them or below them? But some operators do have, different, different choices, different choices available to them if they do not already have like a full zone development on that. So there's both the potential optimal, and then there is the, okay, given what's already there, what's the optimal? So we're excited to be expanding our work on that on the feature engineering work that we're doing. Good question. Okay, so Ryan Campbell asks, with a lot of potential confounding variables, how do you think we're getting such encouraging results with these new causal models? Well, it's because they're designed to deal with the confounding variables, like literally within their, within their architecture. So, I mean, I will say, like beforehand, if a lot of times in order to get proper spacing sensitivity, we might have to filter down to a very specific area, and even then, it might not properly capture what's going on. It just kind of depends on the data that's present for any given operator or any given area. But these are really giving us awesome results for sure. Okay, Henry Galvez says, causal models are constructed using directed acyclic graphs. Have you validated the DAG, identifying confounders and treatments? Can the DAG be modified as necessary? So it's probably beyond my pay grade to speak exactly to that, but we have looked at various different architectures for treatment variables and baseline variables, things like that. And we do not give, right now, we don't give any ability for our users to modify the internal architecture of these causal models. Eventually, we will probably do that beyond some of the other choices, just around like which features go into it. Okay, so then I have a question. If we can, from Ahmed, if we can share the recordings and any accompanying notes, definitely we will share you the recording. So thanks for that one. Okay. So next we have a question from Sumir. You showed parent cum and parent vintage as primary variables here to show child EUR per foot. What are other dominating variables you're observing that impact child EUR per foot? Yeah, certainly, like the other things that will affect the production are a lot of what you would expect. What is the completions intensity of the child well? What's the geology, like clay volume, oil in place, thickness, depth, things like that affect, or that are present at the development. All those will have an impact. Distances to various co-developed wells will have an impact. Lots of different things. So I actually here I can pop over and show you. This is for my regional model that I was using for that infill study that I was just showing you here. So I can like look at my, I put 16 different features into this model. So you can see how those different variables impacted this model in particular, where they're ranked by the explanatory value of the variable to the model forecast. So I will say with parent-child, it can get more and more complicated, and we are we're still doing a lot of research into different ways to featureize like the parent production to give the models the most informational value as to the depletion. Yeah. So while I'm here, I went ahead and pulled up the software. I'd love to show you guys how this actually works here live in the software for building a causal model. It's very simple. Not all of you have probably actually seen this before, so I'll take advantage of that. But this is the Novi platform here. We have different applications for different use cases, but I'm going to click into Model Engine to start with. And if I want to go build a model, I can hit the create button here. Let's call this one demo model. If I'm wanting to build a causal model, I'm going to need to select the procedural forecasting option. Then I choose my model input, and these are filtered down versions of the data sets that I'm using. So let me click on this one here. This little logo here means that it's built using our Insight Engine data. So that's the data that we go and collect from the different state agencies. So then I choose the different features that I want to pass to the model. So these are, a bunch of them are listed over here on the left. They'll have a little star if they are a recommended feature based on our prior work here. So I can put in things like cash flow ratio, thickness, etc. If I did want to be using a spacing variable, there are plenty of those in here as well, like distance, lateral farther, closest to distance equivalent, days online of the parent distance. All those are available here, and whichever spacing variables that you pass to the model or parent-child variables that you pass to the model will be used by the causal model as a treatment effect. And so if I hit this filter by category drop down over here, I can see all the different variables that are going to be eligible for use in the causal model. Then when I go over to the parameters screen, I have a few options here. Which production streams do I want to forecast? Do I want to be forecasting production normalized by lateral length? What do I want my test group definition to be? So do I want to hold out a random 20% of pads? Do I want to do something time-based or something else? But the causal models, these are down here in the advanced section. So I just hit that little toggle right there and go and I select my causal model. So once that's done, then I can save and build my model, and it'll send me an email when it's done. And if I wanted Scott to get an email as well, because he's working hard and I need him to process this really quickly, I can just go ahead and fill that one in. So I'm going to go ahead and cancel out of this one to avoid building it actually. But once you've built these, then you can kind of track whether or not you built a causal model or a standard model using this model type here that you see listed in the table. And the other thing that I will share about these is the causal models do take longer to build than a standard procedural model. Yep, where the standard procedural, that thing might build in an hour, depending on the size of your model, 3 hours, 4 hours, size of your model, number of features, feature selection, etc. But a causal model that could take up to 24 hours to build, just because it's a bit more complicated and processing intensive than the standard model. Okay, got another question here from Samuel Rogers. Have you experimented the treatment design impact on the result? I'm not exactly sure what you mean by that question. Feel free to drop a clarification in the chat, but we have done a lot of experimentation on varying the treatment effects and how that impacts the forecasted production. And then Ryan Campbell asks, are causal variables limited to spacing type variables? If so, why? Yes, they are, at least for our current implementation. And this is just because behind the scenes, it's rather complex how it's wired up to define which variables are treatment effects and which are not. And so eventually we would love to use these for other variables as well. Like you could imagine, maybe artificial lift type being an example treatment that could be applied to a well or something like that, or I don't know, a certain coating on your proppant. So something like that, maybe the types of problems that you would go after with this type of algorithm. So eventually, we would probably like to do that type of a thing, but right now, as you've seen, it's just a little button that you click inside the model. Okay, so then Steve has another question here. Is the debiased data available for inspection, or is it pipelined in situ to the ML engine? It is all in situ, so we don't expose that right now. It's I'm sure somewhere there's an S3 variable, but yeah. Yeah, certainly geology. That yeah, there's a ton of things that could be looked at potentially as a treatment variable here. I mean, and the other reason, Ryan, just to be perfectly honest, why we just went ahead and did these for spacing type variables is the models did really pretty well for geology and completions, like no problems there. Whereas spacing and parent-child was a bit of a harder problem to tackle. So that's the other reason why they're only enabled for the spacing variables right now. Yep. Yeah, you're very welcome. Okay, we got 18 minutes left. I'm happy to take any more questions that you guys had. This is a great conversation. Really love all the questions that we're getting and the attendance today. I'll give you guys another minute or two if you want to type anything more in there. I'll be here. I'll be here till 11 o'clock, so you may as well ask the question if you have them. Thanks for keeping Ted on his toes. Yeah, that's good. That's good. It's a lot of fun. I mean, we're really excited about these. It's the first major algorithmic overhaul we've had in a long time. We've been spending a lot of time, working on the input data and doing things that go around the algorithms, like confidence intervals or Shapley values, spacing calculations. But this is really the first big algorithmic innovation that we've released in some number of years. And I should also say this is patent pending. So we have submitted our patent on it, which is also very exciting. Okay, got another question here. Have you compared SHAP values with and without debiasing and see which parameters it impacts most? Yeah, definitely. I mean, there's a lot of a huge impact on the spacing variables. Let me try a whiteboard here. Let's see if I can find this here. Well, I'm just going to draw here on my screen where we may have, let's say we have some measure of, let's say, just distance to a neighbor, just to be a very simple one here. You guys like my handwriting? That's good. And then we have the impact, the SHAP impact on the y-axis here. So we may have had, like, in a Novi model beforehand, maybe you have that type of a relationship where you have, maybe it even goes up a little bit over here, maybe. So what I'm trying to show is that, like, maybe this is an area where you have, like, relatively limited data, or those development tests are only in a certain area. So you have that high degree of confounding with the rock quality or something like that. Whereas then I come back with, the causal model, I might get something that actually kind of properly captures the full degradation, even over to the edges. So I guess at the end of the day, what I'm trying to say is, like, a lot of times the impact might look fairly similar where you have a lot of data and a lot of data that's widespread around the basin. But as you get into the kind of thinner part of the distribution, and really, it's both the thinner part of the distribution, and it's really where, this is where the money is in terms of the big dollar options for your development options. So, but the other thing that we have seen there, let me clear out my drawing, is the variables definitely go up. They go up the tornado chart when you're using a causal model compared to other ones. So that's definitely a huge impact that we've seen. Okay, more questions. Keep them coming. Are you running multiple treatment variables at the same time, and how are we validating these models? Yes. So the architecture and the approach that we have chosen allows us to use however many treatment variables we want. I'm sure there is a practical limit, but we haven't really run into it yet. And that allows us to, like in this case, you see for this model, I have 1, 2, 3, 4, 5, 6, 7 different treatment variables out of my 16 total variables. So yeah, it doesn't adding in incremental treatment variables doesn't appear to have a big impact I will say the one thing that we have noticed that these models do tend to prefer a more of a regional data set than a focused area. And I think that's just because it gives them a lot more examples, to learn from around the basin compared to, if I just built a model in, I don't know, Martin County, let's say. And then the second question is, how are we validating these? Which is a very good question. And for the validation, we've done a couple things here. We've done a couple things. So number one, we're always looking at error scores on held out test sets. And for these, we will stratify our test and our training sets differently to see how it performs on different ways of generating a test set. So we've looked at obviously the random pad based. We've looked at the time machine based, where we use a certain cutoff date and put things after that date. And then we have also, especially for these causal models, looked at how they have performed on withheld tight density tests. So like one example that literally we look at all the time is how well do these models do at forecasting the dominator pad. And the causal models cut our error on the dominator pad in half. So that's pretty sweet. And then we have other examples, like we've been working very closely with some development partner customers on these models, and they've shared us, hey, here's 10 pads around the basin that we are of interest in that have something interesting going on from a development density or parent-child basis, and how do the causal models perform on those wells compared to a standard Novi baseline pre-drill model. No. And we got another one. Will you quickly redefine treatment variable? Yeah, so the treatment variables are really what the causal inference is estimating the effects of. So let me go back to my slides here really briefly, where we are, in this double machine learning approach that we're taking here, there are some models essentially that create a baseline forecast, and then there's a second model here that estimates the treatment effects. And so those in this case, treatment variable, like that comes out of public health or economic fields, where like literally can refer to a treatment like stop eating red meat, or take an aspirin every day, or give people a tax cut. I don't know, things like that. And so it's but in our case, we're using them exclusively for parent-child and spacing features right now. Maybe more to come on that later. Okay, so Oliver asked, can users define hyperparameters like the ML model and learning rate and the double machine learning? So we don't really expose much option on the hyperparameterization for the machine learning model and the learning rate. Eventually, we may add in more of those, but right now it's kept relatively constrained. And really, that's like, we just want our users to be successful. So we have it right now restricted to areas where we know the models will be successful. But like our general perspective on this over time is to open up more of those types of knobs to our customers as we become confident that they can be successful. And then the follow-up part of your question, does the model assume a linear model to obtain the treatment effect parameter? Yes, we are actually using a series of linear models for the treatment effects, which is another key difference compared to the kind of inferential baseline models that we've been using. So that's why you see these kind of linear effects here on the Shapley plots. One other follow-up on that one is that we are doing work to engineer these features to be nonlinear, to have nonlinear effects as well, although that has some trade-offs. So certainly. And then we got another question from Henry. How many treatments are being considered in causal evaluation? I believe these are multi-treatment causal models. We can have as many treatment effects as spacing features that the user provides, and we haven't really run into an issue with having too many of those, at least so far. Of course, I say that I'm sure that one of our customers here on the call is going to go out and try and prove me wrong and run a model with 35 different treatment effects and just see how it does. But I don't know. Let us know how it goes if you go do that. If you do go do that. Cool. What else? We got 9 minutes left on the clock. Got plenty of time if anybody has any more questions. I'll give you another minute or two to ask them if you have them. But pretty good. We still got really good attendance going through here, even after all the slides are done. So we definitely appreciate that. Good. Okay. Well, last thing that I'll plug, if you are in Denver tomorrow, the SPEE, not the SPE, our lead data scientist Dylan Niederhut is giving a talk there on causal modeling and on parent-child specifically. And then in all likelihood, we're going to have a bunch of ERTech papers on this next year. We're working on these. So those will be definitely something for you guys to look for in next summer when those are out. Okay, well, thanks everyone for spending a part of your morning or your afternoon with us here today. We really appreciate getting to share the stuff we've been working on with you. It's really incredibly valuable for us, and I mean you can probably see my enthusiasm for these new algorithms that we have out there. So it's really exciting. But with that, we'll conclude the webinar. We'll be sending out a recording afterwards if you want to go back and take another look on your own time or share it with your colleagues. So thanks again, everyone.